Hello, it's Belinda Merkelis back for week 2 with Group Three's reading Rote versus Meaningful Learning by Richard E. Mayer. This article was published in 2002. Let's get started. Learning involves the acquisition of knowledge. Mayer, page 226. And how one defines that acquisition of knowledge has changed over time. Traditionally, learners were presented with information in books or lectures, and they were assessed on how much of that material they could remember. But a revision to Bloom's taxonomy has required educators to re-examine what it means to acquire knowledge. In the previous version of Bloom's taxonomy, educators who assess students on how much they remembered from a text or lecture were focusing on the remembering level of the taxonomy. But that level has limited the cognitive processes because it is only promoting the retention of information. With the newer version of Bloom's taxonomy, there is an impetus to move beyond retention and into transfer of knowledge, which includes utilizing learned information to solve novel problems. Stated somewhat differently, retention focuses on the past, transfer emphasizes the future. Mayer, page 226. Mayer then goes on to describe scenarios of no learning, rote learning, and meaningful learning, and how the new levels of Bloom's taxonomy include 19 cognitive processes within its 6 levels that are more suited to transfer of knowledge and therefore lead to meaningful learning. The 19 processes are under remember, recognizing, and recalling; under understand, interpreting, exemplifying, classifying, summarizing, inferring, comparing, and explaining. Apply includes executing and implementing. Analyze, differentiating, organizing, and attributing. Under evaluate, checking, and critiquing. And lastly, create, including generating, planning, and producing. The rest of this presentation will be dedicated to these processes and their application for instruction. But first, let's start with rote learning and meaningful learning as Mayer presented them. Mayer defines rote learning as possessing relevant knowledge but being unable to use that knowledge to solve problems. This is one step above no learning, in which a student has no knowledge base or process for solving problems, and one step below meaningful learning. Mayer defines meaningful learning as a learner possessing relevant knowledge and is able to use that knowledge, transferring it to new problems. What are the key differences between rote learning and meaningful learning? The key differences between these two types are best demonstrated by a case study of each type of learning, as Mayer did in the article. Let's follow Amy, Becky, and Carla as they attempt to learn circuits in their science course. For the no learning scenario, we follow Amy, who skims a textbook chapter on electrical circuits. Amy then takes a test and can recall a few key terms, but overall does not retain enough information to list the parts of a circuit, solve problems relating to the circuits, or construct an essay answer about an issue with a specific circuit, even though all the information needed to do so was presented in the text provided. This is a worst-case scenario for instructors and learners, as knowledge is neither retained nor transferred. Thinking of your own teaching practices, are you reminded of any student that is stuck in this no learning cycle? I'm sure we've all seen this learner before. We will see later in this presentation practices that encourage the student to move towards meaningful learning. Next, we follow Becky. Becky carefully reads the same textbook chapter and takes notes on the material, practices by reviewing her notes and memorizing facts. Becky can recall key terms well and list the components of a circuit, but she, like Amy, cannot answer an essay diagnosing an issue with a provided circuit. Becky has retained some knowledge, but she did not fully understand it and could not use it to analyze a problem. her knowledge was just memorization of facts or rote learning. It seems that this student could be successful in completing a course that is designed with only remembering and recalling facts as its main goal, but would struggle applying that information to future courses or in their career path. Again, reflecting on your own teaching practices, are you able to recognize rote learning characteristics in your own learners? Again, I'm certain we've all seen these students. For me, it's the ones who can answer multiple choice questions that are biology vocabulary word based, but cannot use those vocabulary words to describe a process. Later in this presentation, we will find ways to encourage meaningful learning for these learners as well. Finally, we follow Carla, who reads the same textbook chapter carefully and thoughtfully. Carla is able to recall key terms and components of a circuit and answer the essay question about the issue with the provided circuit because she fully understood the material and is able to transfer that knowledge to solve problems. This is an example of meaningful learning. This student seems to not only have that solid base of knowledge of the facts needed, but can solve problems both in this class and potentially in the future. This is a best case scenario for the student and the instructor. Again, considering your own teaching practice, do you know any students that are already meaningful learners? Next, we will focus on the cognitive processes that will allow instructors to facilitate this type of meaningful learning for their students. What are the cognitive processes that are involved in meaningful learning? There are a total of 19 processes. Let's take a brief look at each one. The first level in Bloom's taxonomy is remember. Remember includes retrieving relevant information from long-term memory. The cognitive processes used in remember are recognizing or identifying, which is when a student can locate information from their long-term memory that is consistent with readings and presentations, and recalling or retrieving, which again requires locating relevant information from long-term memory. The type of objectives that are consistent with recognizing, for example, would be to identify the exports of South American countries, and then the assessment would be a multiple choice question where students choose the major export of Colombia. In recalling, an objective might be to recall the poets who authored different poems. Then a question might ask, who is the author of a certain poem? As an instructor for an introductory biology course, many of our course objectives do fall into the recognize, recall, cognitive processes. This is something that I am now more aware of after reading this article. As we will see, these objectives are still needed to encourage students to have meaningful learning experiences, while they themselves focus more on retention. Think about your own teaching practices. You may find that you have some objectives that fall into this category too. Again, both of these processes are more involved in retention of knowledge than transfer of knowledge. And while that remembering of knowledge is still essential for learners to have a knowledge base, it should be tied to problem solving and complex tasks so that learners are moving toward meaningful learning. Let's look at moving to meaningful learning with the other levels of Bloom's taxonomy. The next level is understand. Understand includes interpreting and exemplifying. The understand through create level of Bloom's taxonomy makes learners construct meaning from instruction, including oral, written, graphics, lecture, readings, demonstration, and computer models. Mayer argues that this is where the transfer-based education objectives are emphasized, and these cognitive processes from understand to create do just that. If we look at understand, the cognitive processes include our interpreting, exemplifying, classifying, summarizing, inferring, comparing, and explaining. Learners are able to call upon their past knowledge base and make connections to the new knowledge being gained. As instructors, the impetus is to create objectives that require learners to use these higher cognitive processes. Interpreting, for example, is also called clarifying, paraphrasing, representing, or translating, and it includes learners being able to take information from one form and represent it in a different way, such as writing algebraic equations from word problems. Exemplifying or illustrating and instantiating happens when a student is able to find a specific example of a generalized concept. An example would be for students to be tasked with identifying various artistic painting styles and then being assessed on their ability to find a new example of an impressionist painting not mentioned in class. Upon reflection of how these objectives are used in my current biology courses, I found that we most often use them in our laboratory courses, where students are interpreting graphs or tables in order to identify the question, hypothesis, or variables in an experiment. Also, under understand is classifying, summarizing, and inferring. Classifying happens when a student determines something belongs in a certain category. An example may be that students are asked to classify different cases of mental disorders in a social studies class. And then students watch a video with a mental patient expressing behaviors, and they are asked what disorder is being displayed based on that behavior. Summarizing occurs when students are able to create short statements that describe the theme of the presented material. Students may be asked to summarize events portrayed pictorially, and then they watch a video and provide a summary of the events. Inferring happens when students draw conclusions from the presented material, such as being presented with Spanish grammar rules on the articles el and la. Students formulate a principle for when to use each article. How do these three objectives and processes show up in my biology courses? Well, there are many ways. For example, my students are put into small groups and given a box of things that are pictures representing items that are metal, plastic, bone, plants, mushrooms, animals, protists, and more. They then must classify these items as living or non-living. Once they've classified their items, their group must come up with rules as to why they placed an item into the alive or the not alive category. We then cover a chapter section on characteristics of living things, and at the end of class that day, students have an exit ticket where they must summarize the characteristic of living things in their own words. Not only is this activity hands-on and fun in our lecture time, it is truly using all three of these understand cognitive processes. Under understand, we also include comparing, or called contrasting, mapping, and matching, which is defined as detecting similarities and differences between two or more ideas, and explaining. For comparing, this could require students to compare a new piece of knowledge to something that they are already familiar with, like comparing the Revolutionary War to an argument between friends. In my biology course, I have students compare cell organelles to parts of a city, where the nucleus is the city hall, the Golgi apparatus is the post office, and the mitochondria is the electric plant, for example. Explaining or constructing models is mentally constructing cause and effect models for the presented material. You may see an objective that asks students to observe a natural phenomenon and use physics laws to explain it. That concludes the understanding category of Bloom's taxonomy. Next, we move to apply. Apply is this next level, and it requires learners to procedurally work through problems and exercises. The cognitive processes include executing, which is carrying out procedures for a task, and implementing, which is applying procedures to an unfamiliar task. Executing is then seen to rely on retaining information, and implementing relies on the transfer of information. And both use some understand as well as the apply cognitive processes. An example for executing would be to ask students to learn to divide whole numbers by one another. And the assessment would look like giving students a worksheet with 20 division problems. Implementing could look like asking students to use the most cost effective method for a research study. And then you would assess by providing a scenario and asking students to propose a research product that meets cost and effectiveness criteria. In my biology class, these two processes are most commonly found in our lab work. For example, students are taught how to use micropipettes and then are required to practice their pipetting with a worksheet that verifies their accuracy. Later in the course, they are then asked to use those micropipette skills to measure restriction enzymes and DNA from solutions to successfully complete a gel electrophoresis experiment. Next on Bloom's taxonomy is analyze. Analyze is the goal of many fields of study, and naturally it looks different based on the content of each class. In order to analyze, learners need to be able to break information into parts and determine how they are related to one another. The level analyze includes differentiating, when students are able to pick relevant from irrelevant information from learning materials. When students then discover how these elements fit into a structure, that is called organizing. And finally, attributing, which is when learners are able to determine the point of view, values, bias, and intended meaning from learning materials. These skills are seen as important to hone as they are an extension of the understanding level of taxonomy. Examples of differentiating could include asking students to select relevant numbers in word problems, and the assessment would be having them circle those relevant numbers. For organizing, students could be given a passage and tasked with creating an outline that shows facts that support the conclusion that the American Civil War was an urban versus rural conflict. And finally, the attributing skill, students may be asked to determine the point of view of authors and then tasked with analyzing a text about the Amazon rainforest to determine if it has a pro-environmental or pro-business perspective. In the courses that I teach, I find that we are very good at the differentiating and organizing, but we struggle with attributing. There are natural extensions of this level of Bloom's taxonomy and the cognitive processes mentioned in the biology world. We model differentiating important information in our presentations by using bold and different colored text for vocabulary words, and we teach students to underline or circle those words while working through classwork or exams. Students organize the events of photosynthesis and cellular respiration by noting the starting reactants and end products in each step. The area that we do not focus as heavily upon is attributing. Future work in our department could include using course material related journal articles or science communication stories, and I welcome other suggestions from the members of this class. Evaluate is the next level of Bloom's taxonomy. Evaluate refers to making judgments based on a set criteria. Evaluate includes checking, coordinating, detecting, monitoring, and testing, which is determining the errors or inconsistencies in procedures or products. A student may be asked to determine if a scientist's conclusion follows their data, and may be assessed by having a student read a lab report and then determine if the conclusions are presented by the experimental data. Critiquing, also known as judging, is when a learner can not only see the inconsistency or errors in the procedure or product, but can then judge the effectiveness of the product or offer some other solution. In Mayer's example, students are given the objective of evaluate a proposed solution to a social problem in terms of its effectiveness. And then they are given the problem, eliminate all grading as a solution to improving K through 12 education. In my science course, checking and critiquing are also heavily emphasized during our lab time. Students create lab reports that must be peer checked for errors and so that the conclusions match the design and data presented. And students must constructively critique, offering suggestions for improvement in design and presentation. In doing so, we hope that students are then able to look at their own work with the lens of checking and critiquing as well. Mayer argues that critical thinking lives within this checking and critiquing. Lastly, there is the level create, which includes combining items together to make a whole product. And then we have generating or inventing new ideas, planning or designing, which is designing a way to reach a goal, and producing or constructing, inventing a new product. The creative process includes three components, according to Mayer. It includes problem representation, solution planning, and solution execution. The cognitive processes listed under create then follow those processes. Generating, again, inventing an alternative hypothesis based on the criteria given. This goes beyond knowledge that the learner already has into more abstract thinking, and therefore we can even call it creative thinking. In this way, it is like problem representation because it allows the learners to try to understand the topic and come up with many solutions. Planning or designing is devising the method to accomplish the task. Sometimes this step is provided by the instruction, such as class time being dedicated to each step of a project. It can also be implied, such as you turn in a final project and the student had to plan how to complete it within the time frame. And other times it is assessed as submitting a schedule or a rough draft to be edited later. An example of how planning is seen in the classroom could be that students are asked to list the steps needed to solve a geometry problem, and then the assessment is that the accuracy of that list. This is mirroring the second step of the creative process, as the student will create a workable plan. Last is producing or constructing, where students will invent a product. This could look like a goal to design a habitat for a purpose, and then a project where students design a living space for the space station. With all of these processes under Create, very specific grading criteria or a rubric is necessary for assessing the students. That way, students will know the constraints and the criteria they are being assessed on. Producing mirrors the final step of the creative process as students execute a solution. In reflecting on my own teaching practice, I feel that our biology department does not focus much time in this level or its cognitive processes, aside from students planning and producing their lab reports. Future work could include finding ways to incorporate these objectives into our lecture portion too, perhaps with a unit project. Again, I welcome suggestions from the members of this course. Phew, that was a lot. While the above list is a long list of cognitive processes with short definitions, for this summary, Mayer concludes that diving deeper into these cognitive processes and where they fall on Bloom's taxonomy has many implications for teaching, including class objectives and assessment design, as well as the goal for design and instruction to become transferring knowledge, not solely retention of knowledge. Let's take a further look. How do these processes contribute to better retention and application of knowledge? As a whole, these processes allow for learners to move beyond that rote learning into meaningful learning. As previously mentioned, students will still need some remembering in order to have a base knowledge for transfer of knowledge to occur. So it is still important to include these cognitive processes in your course design. If we look at our guiding point, let's more specifically look at understanding, applying, analyzing, and creating. Recall that understanding allows students to construct meaning from their educational materials. Therefore, there is a building of new knowledge into the framework that the student already knows. This personalization, through making connections to information students already have, moves them from remembering into being able to apply that information. Recall that applying means to use procedures to solve problems, and it is in that procedural knowledge that students apply or transfer knowledge. Again, recall that analyzing is breaking material into parts and determining how those parts are related. Instead of strictly remembering the parts, students must differentiate important and unimportant components and draw conclusions, again, moving them into transfer of knowledge and meaningful learning. And lastly, with creating, students are able to put together many elements in order to create a whole. They must use all the previous cognitive processes to be able to be successful. What are the implications of Meyer's findings for instructional design? Well, Meyer highlights that the importance of educational objectives utilizing the cognitive processes involved in transfer of knowledge that fall into understand, apply, analyze, evaluate, and create. It is also important to recognize that assessments can be broadened to allow students to demonstrate not just recognize and recall under remember, but should include all 19 cognitive processes. The question then becomes, what does that look like? Imagine a science class that you took in your undergrad career. How were you assessed? If it was anything like my experience, it boiled down to a multiple choice midterm and a multiple choice final exam based on recalling content information. Think about how much of that information from that course you remember and use today. For me, until I began teaching myself, much of the information I learned in those introductory courses was lost. Now imagine a college course where there are different opportunities to show what you've learned. Not only multiple choice exams, but demonstrations, projects, papers, along with those exams. Think about how much more a student will be able to remember and use with these different processes being expected of them. This is the challenge we are being given as instructors to design courses with assessments that go beyond recognizing and recalling and into active, meaningful learning. How can educators promote meaningful learning in their classrooms? Well, this is a very important question to ask. And while the content is different for each subject, the idea of moving from rote learning to meaningful learning by utilizing the cognitive processes laid out in the new Bloom's taxonomy previously mentioned in this presentation to create objectives and varying assessments to evaluate student performance is the way that Mayer suggests in this article. In the biology department where I teach, there has been work toward this goal for some time, and we continue to revise our objectives and assessments, but it is a continual process. We began by looking at our course and the chapter level objectives and making sure to vary the level of Bloom's taxonomy. This has then led to incorporating different assessment to match those new objectives. For example, we previously had two objectives: list cell organelles present in a typical plant cell, list cell organelles present in our typical animal cells. This has now been updated to compare and contrast organelles found in plant and animal cells. Students are then given a Venn diagram to fill in with organelles that are found in plants, organelles that are found in animals, and organelles that are found in both plant and animals. In what ways can you analyze the objectives in your learning environment and design assessments to move students to transferring knowledge? Thank you for watching this presentation. I hope that you enjoyed it, and I look forward to your questions. Have a wonderful week, everyone.